Hello everyone, I'm Rodrigo. I'll be talking about nonlinear equalization in 112 gigabit per second passive optical networks using Kolmogorov-Arnold networks. I start by introducing a little bit of context, and in passive optical networks, typically IMDD is employed due to its associated lower hardware costs and also complexity. In the IMDD context, PAM4 is set to drive higher line rates. However, this comes with higher signal-to-noise ratio requirements and also lower tolerance to system nonlinearities and impairments. Now, to illustrate where these nonlinearities and impairments are in a typical IMDD system, I'm going to show you the diagram for the setup we had in our lab. At the transmitter side, we have an electroabsorption modulator that has a nonlinear transfer function. After modulating the laser beam, it gets fed to 2.2 kilometers of standard single-mode fiber, where it accumulates chromatic dispersion. However, since we are performing direct detection by a photodiode, this manifests as a nonlinear effect. Also at the receiver side, we have a semiconductor optical amplifier that exhibits gain saturation, and in contrast with constant gain, the gain saturation of the SOA is a nonlinear effect. And since we have so many nonlinear impairments in the system, we need to use nonlinear equalization, as it will become clear with our results in the end. Some existing solutions for the equalization task in passive optical networks include linear FIR filters, but also some examples of nonlinear equalizers are Volterra nonlinear equalizer, recursive neural network, and convolutional neural network. And in this work, we explore the use of Kolmogorov-Arnold networks for the equalization task. Kolmogorov-Arnold networks were recently introduced in May 2024, and their main characteristic is that they allow for interpretability of the learned network models. However, it was also observed that to achieve the same performance as a CNN, a CON with a smaller number of neurons was sufficient. In the present work, we analyze the potential of reducing computational complexity of CONs. However, we leave the interpretability of the trained equalizer as future work. But before I can actually talk about Kolmogorov-Arnold networks, I'm going to give you an example of a convolutional neural network-based equalizer used in feed-forward equalization. It's quite straightforward. We start with the non-equalized samples that get convolved with a kernel, and until this point we just have a simple FIR filter. However, in convolutional neural networks, we use a nonlinear activation function, which also makes this equalizer nonlinear. And in order to achieve better equalization performance, we add multiple layers or multiple stages of filtering with nonlinearity. Similarly, in Kolmogorov-Arnold networks, we start with the non-equalized samples. However, we replace the filter taps by learnable scalar functions. So this means that the kernel will still be convolved with the inputs in the sense that it will be shifted, and then the sum will be performed after the inputs have gone through the functions. However, instead of just multiplying the inputs, we run them through scalar functions that should be trained or adapted. And just like in regular CNNs, we stack multiple layers to refine the equalization process. And an important question that arises now is how can we implement the learnable tap functions? And the way that was proposed in the literature is to use shifted sums of a basis function scaled by some linear weights. This is better visualized by an example, and in the present work we used the triangular function as a basis function. We have here 5 copies. The first copy is at -4, and then the subsequent copies are shifted by a value delta x of 2. And since they are triangular functions, after scaling them with some weights and summing everything up, the final result we have is just the interpolation of the weight values where the functions are centered, which I call grid points. It's important to notice that the linear weights are the trainable parameters of this function. However, the number of points or the number of basis functions used, g, and also the initial offset and the increment delta x are design parameters. Furthermore, the final function is a piecewise affine function, meaning that we have the advantage of only needing one multiplication for every evaluation of the function. However, this comes with a trade-off because we need to first perform a lookup step to decide in which interval of the piecewise function we are, and second, we need more memory to store the corresponding affine function values. We follow our presentation by presenting some more design parameters we can tune. In our equalizer architecture, for example, the stride of the convolution, the number of kernels or number of channels, and also the kernel size. And in order to find out which combination of design parameters yields the best equalizer architecture, we perform design space exploration. And to do that, we collected data using the experimental setup shown before, where we used a VOA to set the received optical power from -30 dBm to 2 dBm. For each ROP, we measured 30 sequences of 2.8 times 10 to the 6 PAM4 symbols at 2 samples per symbol, so that we can perform averaging over multiple sequences. And then we split each sequence into training and testing subsequences. The size of the testing subsequence is only 70,000 symbols, and we perform offline learning, that is the update of the tab functions using the mean square error loss. And after the equalizer has converged, we measured the bit error rate on the test sequences. And what this gives us is a scatter plot that looks like this. In the x-axis we have the real valued multiplications per symbol, so the number of real valued multiplications per symbol required by each design, and it actually has a complicated dependency on the stride, the kernel size, and the number of kernels. On the y-axis we have the bit error rate. Each point in this scatter plot is a different network design. However, we can see that there is an optimal trade-off between bit error rate and real valued multiplications per symbol, which is a proxy of the computational complexity of our equalizer. And this optimal trade-off is called the Pareto front. And furthermore, I illustrate here by changing the markers I use how the design parameters actually affect performance. So for example, if we use a higher number of kernels in the first layer to process in parallel features of the input signal, we obtain a better bit error rate performance that comes, however, at a higher cost of real valued multiplications per symbol. And using the Pareto front, we can actually compare different network architectures without taking into account specific design choices. And we do that, for example, to compare a CNN with 2 layers, a CON with 2 layers and 5 grid points, and a CON with 2 layers but a finer grid with 9 points. And we can see that for this application, choosing 5 grid points is sufficient. We also see that there is a considerable gap between the CON and the CNN. And from this point, we can further optimize our models by performing something called pruning. By performing pruning, we remove the weights or the activation functions that don't contribute much to the equalization performance. And we do that by selecting the weights or the activation functions that have smaller magnitude, and we set them to 0. After pruning, these are the Pareto fronts that we observe. We observe that there is still a performance gap that narrows down in this region between the CNNs and the CONs, but we also observe that to achieve a bit error rate of 10 to the minus 4, before we needed around 300 RVMS for the Kolmogorov-Arnold networks, and after pruning, so after removing redundancy from the equalizer architecture, we need around 200 real-valued multiplications per symbol. And this illustrates the importance of pruning in such equalizer designs. Now, we analyze the performance of some selected designs, and we are looking at computational complexities of 21 RVMS up until 321 RVMS. And to choose the designs that we are going to test across a certain range of received optical powers, we selected them using the Pareto front at the corresponding complexity. We are analyzing linear equalizers, represented here by FRL filters, CNNs with 2 layers, CONs with 2 layers and 5 grid points, and CON with 1 layer and 17 grid points. We see that if we don't have a large computational budget, if we only have 21 RVMS, we can see that the relative performance between the analyzed methods is quite close. However, once we increase our computational budget to 321 real-valued multiplications per symbol, we can see that there is quite a performance gap between the best performing model, the CON, and the worst performing model, the FRL filter. We can also observe that all the nonlinear equalizers were able to outperform the FRL filter, showing the importance of nonlinear equalization for this task, especially because the linear equalizer performance saturates at around 121 RVMS, since by increasing the computational budget to 321 RVMS, its performance doesn't change much. We also see that notably, the Kolmogorov-Arnold network with 1 layer was able to match the performance of a CNN with 2 layers across the complexities up until 121 RVMS. And we also see that the Kolmogorov-Arnold networks with 2 layers had the best performance out of the tested models. And this brings me to the concluding remarks. We showed the importance of pruning and design exploration to optimize the computational complexity. We also showed that the novel Kolmogorov-Arnold networks are able to outperform CNNs as equalizers in PONs at the same computational complexity while successfully compensating for the nonlinearities. Thank you very much. And if you have any questions, please contact me via email.